룰을 설정하고 그리고 그 룰이 반영되는 걸 눈으로 확인할 수 있는 부분이 좋았고, 플렉스 툴은 저희 전사의 표준 툴입니다. PCB 설계하거나 아트워크 하는 사람들, 그리고 기존의 회로를 설계한 하드웨어 엔지니어, 그리고 제조 쪽을 관장하는 사람들, 그 다음에 일부는 우리가 과제 프로젝트 리더들도 같이 꼭 사용을 하고 있습니다. 회로 쪽 관련해서 플렉스를 사용하는 인력은 100여 명 정도 되고요. 이제 제대로 검증이 됐는지 이렇게 회의체나 이런 걸 통해서 뷰어를 사용하는 이런 부분도 한 5, 60명 정도 추가가 됐다고 보시면 되겠습니다. 전지는 안정성이 최고입니다. 그래서 회로의 안정성을 가장 중점으로 보고 있고요. 사실은 무혈점 회로를 만드는 게 가장 큰 목표고, 그래서 이 무혈점 회로를 만들려고 하다 보니 저희가 기본적으로 회로 설계 툴하고 그 다음에 폴렉스의 검증 툴하고 좀 유기적으로 연결을 해놨습니다. 그래서 그리고 거기에 적용되는 룰은 저희가 메인 시스템에서 내려받아서 돌아갈 수 있도록 되어 있고, 그 결과물도 메인 시스템에 저장하는 식으로 진행을 하고 있습니다. 아무래도 저희가 소프트웨어적으로 검증을 하다 보니까 기존의 유관 검증에 비해서 사용자의 에러를 검증할 수 있는 능력이 굉장히 뛰어나고요. 그러다 보니까 재설계를 할 필요가 상당 부분 줄었고, 그 다음에 이 재제작까지 이루어지는 분야를 사전에 차단할 수 있어가지고 사실 개발 기간 그리고 제작비 거기에 효과를 많이 보고 있습니다. 빠른 대응, 그러니까 저희가 요구하는 아이템을 정기적소에 바로 제공해 줄 수 있고 저희가 요구하는 대로 수정해 줄 수 있고 그런 부분이 영향을 받았습니다.
And besides this, we also have the mechanical engineers whom with this type of electronics developments, they need to analyze vibrations, drop testing, warping of PCBs, and this is something that they are doing in SimLab, which is our multi-physics platform for electronics, where you can see the workflow, which is pretty straightforward, starting with from the ECAD, simplifying the geometry meshing, and then assigning materials and deciding the simulation to be done. But it's not only for the mechanical simulation. In SimLab for electronics, we can also do the system thermal analysis and the electronics thermal management, including external heating, component heating, and joule heating. On the left, you can see an avionic box, including 3 PCBs. This is a problem that can be solved in around 5 to 6 hours. And on the right, you have a pump controller. This is a case with just 1 board, but the geometry is a bit more complex that can be run in around 30 to 40 minutes. And now we jump to the electrical engineers who are working on the design of the antennas, analyzing which is the best place to where to mount the antennas, also working on the simulation of a drive test or a flight test, working to analyze and mitigate interferences in electric vehicles, or analyzing the communication range in a system. Or also, there are civilian and military organizations working on the management of the frequency spectrum. And from these applications, I would like to recall this use case related to antenna design and placement for Airbus, where basically they are using our simulation technology to know, to ensure the antennas are sitting on the right positions, taking into account nearby equipment, but also constraints, for example, like the maintenance. And this is a very nice case, but now what's next with this? And here, I would like to just briefly talk about digital twins related to wireless connectivity, where here with the digital twin, this is helping to make decisions during the development phase, to optimize the product during its operation, and also to collect data that will be used afterwards to improve the product. And I will use, for a digital twin, a case related to an antenna on a helicopter. This is a customer story from Leonardo. This is a bit more complex. This is because you can see the antenna, and then behind the antenna you have the supports, the motor, the system controlling the motor. So this system is really more complicated. And their goal is to ensure it will have a reliable performance. And to do that, they need to a digital twin, which emulates the real operation of the radar antenna when flying. And to do that, so basically there are two parts. On the right, you can see the data-driven twin, more related to getting the data from the helicopter to do predictive maintenance. And on the left, you have the simulation-driven twin, where here one of the KPIs or metrics is the performance of the radar antenna once flying. And in order to do that, you really need a high-fidelity model where you need to include different physics with the different simulation tools that we have for antenna simulation, control, for electric motors, and for multi-body to improve the performance of the product. And at the end, this is helping them to reduce the time they need to do all the prototyping and also the costs. And also, if we move to digital twins for automotive, we have many customers using our technologies to analyze the connectivity between vehicles or between vehicles and infrastructure. And also this is related to ADAS and 5G, because for example, there is an interesting use case where you have cars approaching an intersection, and you need to ensure that they will communicate with each other to eventually slow down or stop the car. And on the right, you can see something that we are now working on with several customers who want to create, with our technology, a digital twin of the scenarios that they are using to do this type of tests to communicate the vehicle with each other and also with the infrastructure. And now I would like to jump to the last part of the presentation, where I would like to talk about the two most recent acquisitions. One is related to power electronics, because basically today modern electronics means power electronics and power converters. For example, you have to charge the battery, you need to convert AC to DC, or for example, for an electric vehicle, you need to convert DC to a three-phase AC, so for the electric motor. This is a sector which is growing, and it's a key part of electrification. And this is one of the reasons why we acquired PowerSim out of the US earlier this year. Their flagship tool is PSIM, one of the leaders in the market, mainly for electric and industrial drives, used in automotive, aerospace, energy, and some others. And with this, we have been able to really strengthen the solution we have for electrification, which includes lightweighting, battery design, and also power electronics. And a bit more in detail, just to show you a couple of use cases. With PSIM, you can design the control of a motor in minutes, so it's really fast. Okay, and this is used by the motor designers, the power electronic engineers working on the inverter, which is this device doing the power conversion, and also used by the embedded software engineers and control engineers. Eaton is one of the customers using PSIM to analyze the interactions between the devices and the motor as a part of the electric system. And another use case is the creation of a system model of the whole powertrain of either the hybrid vehicle or the electric vehicle to analyze the system, and also where you can do some detailed design of some parts of the system, like, for example, with the electric motor. And just the most recent acquisition is Concept Engineering. This is, I'm done. Yeah, just 1 minute. Okay, this is basically a company out of Germany with technology for visualization and debugging. They are playing in 3 sectors: semiconductors, basically for silicon debugging, so to help with chip design. Also, they have a set of libraries to automatically generate schematics, and this is used by some EDA and CAD software vendors. And the last one is a visualization platform for complex electric systems. This is called eVision, where basically here the idea is engineers and technicians are wasting many hours looking at and trying to find information in a static documents. And with eVision, they have now an online visualization and debugging platform where to quickly render cable harnesses, circuit schematics, and component attributes to enable a smart and design exploration documentation. And there are many companies from the transportation industry using the solution. And one of them is NASA in the US, where basically they have replaced their manually created schematics that they are also maintaining with eVision to reduce time for testing, for design and for manufacturing. And also with eVision, they have been able to have a faster and most reliable development process for these complex electronic systems. And that's all I wanted to share with you. If you want to know more, we have an electronic session tomorrow. And just thank you for your time.
Thank you, Jory. Now we have one more presentation, post which we'll break for lunch. I invite Mr. Livio Mariano, the Director of Math and Systems at Altair, to present on efficient system modeling with reduced order models.
Hi, everybody, and buongiorno Bangalore, like we used to say in Italy. And before starting, and before I forget, I would like to thank Rajesh and Vishwa for inviting me here. It is a pleasure to be with you. Today is my first time in India. Sorry for that. And I'm enjoying it. I'm enjoying people. I'm enjoying also the food. So in this session, I will be talking about system modeling and the role played by reduced order modeling in this field. Let's start with the definition. What is system modeling? Well, you can find many definitions about system modeling, but what it is in summary, system modeling is the capability to model different disciplines and their interaction in the same modeling environment. And let's make an example. Let's considering, for instance, an electric car. And we can see that if we consider this system, that is a complex system, we can identify different disciplines that are coupled together, they interact. For instance, there is the control part, there is a part connected to vehicle dynamics, the part connected to the cabin thermal management, so passenger comfort, battery, BMS, TMS, e-motor, power electronics, and so on. With system modeling, we're able to model all these disciplines and also their interaction in the same modeling environment. Now, a good question is why we want to do that? Well, there are three main reasons. One is connected to the complexity of the problem. The other one is connected to the efficiency. And then there is a third one connected to the collaboration. Let's start with the first. So system modeling helps to have an easy management of the complexity. It means that basically we're able to handle the different disciplines and their interaction. And this is very important. Why? Because in a fuzzy situation where we have different disciplines, we, thanks to system modeling, we can basically find the interaction among them. So we can understand better how our system that is made by different subsystems is organized. And this is very important because it allows a comprehensive understanding of the full system. And this means also maybe the factors that are mostly affecting our phenomena. And why this is important? This is important because this can enable, it can help to generate more ideas. And also, can help to have more creativity. I have found my own Ganesh winking at me in the dots, okay? But maybe this is too much creativity. Now, let's switch about the other topic, that is efficiency. With system modeling, we can simulate hours or days in seconds. Why? Because system modeling use usually equation-based models, reduced order models, or linear models. And if we want to be more specific, so we want to dive a little bit more into the maths, and forgive me for that, the reason is because usually with high-fidelity models, we deal with finite element tools. So basically, we need to solve partial differential equations. While when we deal with system modeling simulation, we need to solve ordinary differential equations or differential algebraic equations, which are much easier and faster to solve. The other main reason of why system modeling is important is connected to the collaboration. What happened, as I explained at the beginning, system modeling is helping to model each discipline and their interaction. Each discipline means that we have different departments inside the company that take care about these disciplines. And this, and because we're able also to model the interaction, this means that basically we're able to break the silos that are in our organization. So it enables a more, let's say, integrated ecosystem environment. That means not just in terms of modeling, but also in terms of teams that are working on these different subsystems. And this is very important, very convenient. Now, how we can adopt this kind of approach? Well, let me share a classification connected to the type of language that we use in system modeling. We're able to basically apply this kind of approach by leveraging the script-based approach, the block-based approach, that is the graphical approach, and the 3D approach that is able to consider an accurate geometry, so the CAD system basically of our system. And of course, what happens is that there is a language that is more suited for specific disciplines. Let's think about control, for instance. In that case, we need to use a block-based approach. But the capability to have available all this language is really convenient when we want to use a purpose-driven modeling approach. Because with this capability, we can model different disciplines with different level of fidelity. Let's think about the multi-body simulation, for instance. I can start with equations, so using the scripting approach. Then I can proceed with a block-based approach using Modelica, for instance. And then I can even consider the CAD geometry of the system with all the flexibilities in the different components. So we can have a really advanced simulation. And of course, in Altair, we have many tools that can take care about this language in the system modeling portfolio that we offer. And here we represent them in a circle because they are all integrated. Let's classify now system modeling considering the approach that we use. There are two main types of system modeling approach, the physics-based and the data-based approach. The physics-based approach really on equations. The data-based approach really on data. What happens is that in the equations-based approach, we need to deal with the equations. So basically, we use a white box approach. In the data-based approach, instead, what we do is to apply machine learning in order to identify the relation that we have among the data. So in order to find a model able to represent the behavior hidden in the data. And this is a black box approach. The two types of approach are different also in terms of steps that we need to follow when we want to apply them. If we consider the physics-based approach, we have that we need to start with the system observation. Then we need to make some assumption, some approximation on the system. Then we need to start to deal with the questions, so to start really to perform the modeling of the system. And then, of course, there is also the analysis of the results. When we deal with so this approach, of course, is accurate with when we deal with the known problem. So when the questions are available and are accurate to describe the phenomena that we want to model. Then we have the database approach. The first step is the same, so we need to, of course, to observe what we want to model. But then there is a step that is different, it's the data preparation. So we need to understand which data are needed, and we need also often to process them before using them directly into the machine learning algorithm. In this case, instead of modeling, in fact, we have the training. So we need to apply a machine learning technique in order to train our model, and then, of course, we can visualize the results and analyze them. Now, this kind of approach, since we do not deal directly with the questions, can be more accurate for unknown problems, and can be even faster to implement because I don't waste time to model the questions here. But of course, let's consider that this is not always suited. Now, let's make an example here. In this example, I want to show the combination of these two approaches, so physics-based and database approach, on a system that is a wheel loader. And this, as you can imagine, is a really complex system with different disciplines that are involved. For this kind of example, I will also present briefly an app that is RomAI. It is an app based on artificial intelligence and is helping us to generate reduced order models. We start with the first step, that is the system of observation. So in this case, we want to take care about these disciplines, that is control, hydraulic actuation, multi-body dynamics with flexible components, and bulk material, that is the handling of the ground, basically. And if we observe this system that is really complex, there are different physics that interact, we can observe that the handling of the bulk material is time-consuming, okay? Because it is a very accurate simulation and with many degrees of freedom that we need to solve. So basically, this is also the bottleneck of this simulation. So the idea here is to speed up this part, these disciplines, creating a reduced order model of this subsystem, and then using it into the full simulation. So the next step is to focus on the bulk material handling, and basically running a few simulations, transit simulations, where we obtain the data needed to generate a dynamic reduced order model that is able to estimate the interaction forces that we have between the ground and the bucket. Once we run this simulation, we can reuse the data into our RomAI GUI that you can see here. And, okay, it is stopping. Basically, what we have here is that we have, the video is not playing, okay, we have an issue, but in summary, what we have is that we can define here which are our input, our output, the state of the system. We can define without any need of code, so it is all done by the GUI, through the GUI. We can define a certain dimension for the neural network that we want to use in order to represent this model. And then we can run the training of this reduced order model. And once we do that, if you go all the way to the end, once we do that, we generate the model. We can even directly estimate the accuracy that we have in this simulation. So we can evaluate how accurate our reduced order model is before using it into a system level simulation. And let's go next. After that we train it, we can use it again into the system level simulation. And we can see on the top left that we have the simulation with the reduced order model. Okay? And you can see that as soon as the bucket touches the bulk material, we have reaction forces that are estimated by the reduced order model. Okay? And in the bottom left, instead, there is the original simulation. What we can see is that by using the reduced order model, we can obtain, if we look at the chart on the right, where we are representing the von Mises stress in the most critical point of the boom, we can see that the accuracy is still really high, higher than 98%. And what is the advantage? The advantage is now that the simulation with the reduced order model takes 20 seconds to run, while the original one was taking 680 seconds. Okay, so basically we have a gain factor in the runtime of 34. So you can understand now the advantage when we need to run, for instance, an optimization. Let's think that we want to optimize the shape of the boom now, or the control system or the hydraulic system. You can understand the advantage, a big advantage that we have following this approach. This is now my last slide, and in my last slide, I want to share, the importance of the artificial intelligence in system modeling. And I want to explain this by using an analogy here. I'm using here the chess game analogy. And by the way, the chessboard is the chessboard of my grandfather, while the dinosaur is from my kid. And artificial intelligence basically is a tool that is helping us to empower our capabilities in terms of modeling, perception, and prediction. Okay? So basically, the analogy here is that artificial intelligence is a new approach compared to the traditional one. Can allow us to perform different moves. Okay? For instance, if you consider here the knight, with the shape of an horse, we can turn it into dinosaur, so it's something that is stronger. In fact, for instance, maybe if we consider the chess game, we can move, instead of 2 squares horizontally, we can move 3 squares, and maybe capture the pawn in this picture. But we need always to be smart in using it. We need to use artificial intelligence when it is convenient, because a rook can be always behind the corner. And why I'm telling this? Because there are mainly 2 groups of people that are really skeptical about artificial intelligence, and others that think that artificial intelligence can help to solve anything. Okay? The truth is in the middle. So there are cases where it is more convenient to use a traditional approach because it is well known, equations are really precise, so it is convenient to follow that path. Other situation, instead, where we cannot use a traditional approach. And in this case, of course, artificial intelligence can help us and play a role. Thank you.
Thank you, Livio. Post-lunch, we shall begin with our technical tracks at around 2:15 p.m. We have technology booths set up outside, so please do visit them for more information on the all 10 new technologies and interact with our experts. We would also appreciate the event feedback that will help us improve the experience in the future events. There will be a lucky draw on the feedback response where one of the participants will be eligible for a prize. So please go ahead and scan the QR codes that are placed outside. Thank you. Also, I would request you all not to leave your bags in the room. Thank you. It's a breakout session, so we will meet at the technical tracks at 2:15 p.m. Thank you.